Hey, AP Chemistry. So I've had a couple of requests and questions about how do I write chemical equations, how do I name them, how do I write ionization equations or dissociation equations, and I feel like it all goes back to this idea of double replacement and how do I know what my products are and who's going where. A lot of this comes in chapters 2 or 3, chapter 2 or 3, and that was some of your summer homework. I would suggest very soon, if you are struggling with how to write equations, you need to go back to that summer work, go back to that chapter and look at more examples. But I'm going to do like an explosive crash course here on double replacement. So double replacement reaction means everybody switches partners. Every element or species that was bonded to something before is not going to be bonded to the same something after. So let's say I have these two compounds here, A, B, C, D. I know they're compounds because compounds have two different elements in there. And something to note here is that they're both aqueous. What aqueous means is that it dissolves in water. So this stuff must be soluble or broken up into its ions in water. So if something dissolves in water, especially if it's ionic, we're just going to make an assumption that these are ionic compounds. If something dissolves or is ionic, we have two different charges that are possible. If I have A and B and I wrote it like A and B, the element on the left is positively charged and the element on the right is negatively charged. And that's always how we write things. The element on the left is positive and the element on the right is negative. Or the species, it could be a polyatomic ion. The species on the left is positive and the species on the right is negative. You need to know that. If I see a compound and I see two elements combined, like if I saw NaCl, I have two elements here. That Na must be positively charged and that Cl must be negatively charged. And it just so happens that that Na is +1 charge and that Cl is -1 charge. And I'm going to go through that later. So you need to know that if I have two elements in a compound, the element or species, the thing on the left is positively charged and the thing on the right is negatively charged. Okay? Now in a double replacement reaction, both of these two compounds that are ionic, because I told you they are going to come together and switch partners. So you need to also know what attracts who, in the sense of, well, positive does not attract another positive, and negative does not attract another negative. So a positive, and I'm going to put that with the circle, is going to be attracted to the other negative, and the negative is going to be attracted to the other positive. So I tried to put like a square over the two things that are going to be attracted to each other, and a circle over the other two things that are going to be attracted to each other. And so if I have this broken up into solution, I might have A plus aqueous plus B minus aqueous plus C plus aqueous plus D minus aqueous. And so why am I writing it like this? This is known as like the Ionic equation. So if I just write out like the simple chemical equation, I could write the Ionic equation. If I have an aqueous ionic substance, it could break apart into its ions. So if AB was an ionic compound like NaCl, that would break apart into its ions. So technically NaCl, if Na is +1 charge and Cl is -1 charge, I would get Na plus and Cl minus, and they're both aqueous. And that's true. Both NaCl, when added to water, can break apart into its individual ions. So if I have an ionic substance and I know it's soluble, that's another big thing. We'll talk about solubility after. If I have an ionic substance and I know that it's soluble in water, it'll break apart in water. That's what soluble means. So now I have all these ions that broke apart. And I'm going to circle the two things that are going to come together, and I'm going to quickly explain why. So a positive is not going to be attracted to another positive. A and C are not going to combine. They are not attracted to each other. But A and D are attracted to each other. This has got a negative ion. This has got a positive ion. So the two of them are going to come together, and I'm going to get A, D. Okay? Then B and C are going to be attracted to each other, because one's a positive ion, one's a negative ion. By the way, a positive ion is known as a cation. A negative ion is known as an anion. The positive and the negative are going to come together, and I'll get Cb. Now, what if you found out somewhere that Cb is an insoluble compound, or under the conditions given here, Cb will be a precipitate, and you could use a KSP, or you could be told with some sort of solubility rule that B doesn't form soluble ions with C. So if Cb is insoluble, I would not write aqueous. I would write solid. And then let's say I didn't know anything else about AD. I could either make the assumption that it's soluble, or I could write AD for aqueous. And what I could do now is I could write this further down and write what's known as a net ionic equation. And this concept or idea is definitely going to help us with acid-base chemistry and the acid-base reactions. But let me just write down everything now. I'm going to start to begin to write a net ionic equation. So I'm going to start here and then end here. So I'm going to rewrite everything. A plus aqueous plus B minus aqueous plus C plus aqueous plus D minus aqueous. And I get, notice how I wrote AD as aqueous. I'll get A plus aqueous. This could break apart because it's soluble. If it's soluble, it'll break apart. D minus aqueous. And then, CB is not aqueous. So I cannot break it up into its ions. CB solid. Now I'm going to look at this entire chemical equation here. Here are my reactants, and here are my products. Products, reactants. Okay? To write a net ionic equation, or a net equation, whatever is present both on the left and right sides, I could cancel them out. So what is present on the both left and right sides of this equation? Well, if I'm just looking and scanning, it looks like I have A plus on both sides. So I'm going to cancel that out. I also look on both sides, and it looks like I have D minus on both sides. But notice how I'm not crossing out my B minus and C plus, because I no longer have B minus and C plus broken up into ions on the right side. So I have a reaction that occurs. C plus aqueous plus B minus aqueous. And I know it looks like I flipped them, but it's the same idea. I could write them either or. And I'll get CB solid. This would be known as the net ionic equation, right? These other ions that I canceled out, these are known as spectator ions. They're spectators because they just float around in solution. They never really come together. They're just hanging around each other. They never really connect and form a solid like the CB did in this case. Okay? So, this is just a crash course on writing chemical equation, double replacement reactions, how do I use aqueous and solid, and what this ionic business means. Let's do an example now. Let's say I'm doing PbNO32 plus NaCl. Now, some of you have asked me, like, how do I name these things? Things like Pb, Na, and Cl, you're going to need to use the periodic table and some naming rules. Metals get named as is. Pt for me means periodic table. Periodic table. So if you use the Pt, Pb is named as lead. This is a polyatomic ion, and you are required to know your polyatomic ions. You need to memorize them or do something with them just in case they come up. But this is NO3, this is nitrate. Okay, Na from the periodic table is sodium. And Cl, now on the periodic table it's chlorine. But if I name it as an ion, the ending ine turns into ide. So this becomes sodium chloride. So the name of NaCl is sodium chloride. The name of lead nitrate is lead and nitrate. And then there's one extra thing about lead, which you're going to have to look back, and we'll review more about what's known as a transition metal, but you're going to have to look back into chapter 2 or 3 how we name. Lead is a transition metal. And according to this equation, nitrate is a -1 charge. That's just known. Nitrate is NO3 -1. It's a polyatomic ion. Its charge is -1. If there's 2 of them, that must mean that this total charge is -2. If I have 2 NO3 minuses, that must mean that this is -2. And the sum of all the charges in an ionic compound, do we know what that must equal? Well, before I told you this was Na plus and Cl minus. +1 and -1 equals 0. So the sum of all the charges in a compound, that must equal 0. So if I have 2 NO3 minuses, and that's -2, that must mean this lead is +2. And since lead is a polyatomic ion, oh sorry, not lead. Since not polyatomic. Since lead is a transition metal, transition metals get Roman numerals for their charges. Roman numerals for charges. Okay, so if you don't know what the heck I'm talking about here, you need to go back to your summer work and you need to look back at some of your summer work examples and in your earlier chapter. Okay, so if it's a transition metal, it needs to get Roman numerals for its charges. So if lead's charge is +2, this is going to be lead 2 nitrate. So the name of these two compounds are lead 2 nitrate and sodium chloride. Okay, now that I've written that, let's try and write a balanced chemical equation between lead nitrate and sodium chloride. Okay, now I'm gonna tell you that these are both aqueous, and they are. Most or all nitrates are soluble, which means that they will be aqueous. Now, how do I know that? In an earlier chapter, there are some solubility rules. You may be given information on the AP exam or in the future, like this is soluble, this is not soluble. Okay, so if it's soluble, I know that they're going to break apart into their individual ions. So I'll get Pb2 plus aqueous plus, now there's 2 NO3s here. So 2 NO3 minus 1 aqueous plus Na plus aqueous plus Cl minus aqueous. I want to figure out who is going to be attracted to who. Well, I have a positive charge here. If I'm doing a reaction where I have 2 compounds coming together, what am I going to call this? I'm going to call this a double replacement reaction. So if I have 2 compounds coming together, this is going to be a double replacement reaction. I have 2 compounds reacting. Okay, so I have a positive ion here. Doesn't matter that it's +2. It could be attracted to NO3, but I'll just get back to where I'm starting before. Is it going to be attracted to Na plus? Not so much, because it's also positive. So this lead must be attracted to Cl minus. Okay, so lead and Cl minus are going to come together. So I'm going to write this down here. This is going to go right here. I'm going to have lead 2 plus and Cl minus somehow come together. And then what's left over is Na plus and NO3 minus. These two are going to come together. So I'm going to have Na plus somehow reacting with NO3 minus. Okay? And there's 2 NO3 minuses. So there's 2 NO3 minuses. Okay? So what do I do here? Well, remember what I said up here, the sum of the charges in a compound must equal 0. So in order for me to write a compound for lead and chlorine, I need to have the sum of the charges equal to 0. Well, if lead is 2 plus, what will I need to get the sum of that to be 0? 2 plus what is equal to 0? Well, that's got to be -2. And the only way I would get -2 is if I had 2 chlorines. So 2 chlorines, so I'd need 2 chlorines, and that would give me PbCl2. Now another trick is, and this is learned maybe in an earlier chemistry class, is something known as the crisscross method. So the crisscross method means I could crisscross the charges, and I just use the magnitude of the number as the subscript. So 1 will go for Pb, and the 2 will go for the Cl. So this is +2, and this is -1, it'll be Pb1, Cl2, and that's where I get my PbCl2. For NaNO3, if I were to do that crisscross method again, Na plus, NO3 minus, it looks like I only need one of each, NaNO3. Okay? So these would be my two products if I react these together. Okay? So now my last thing is if I rewrite this whole thing down, I'll have PbNO3 2 plus NaCl yields PbCl2 plus NaNO3. And notice how before I had two NaO3s and I was like, wait, I only use one, but I have two Cl's over here and I only use one. How can I figure out what to do with this chemical equation to make it correct? I have to balance it. So in order to balance it, let's see, before I had two NO3s over here, and I only have one NO3 over here. So in order for me to balance that, I'm going to need to put a big 2 in front of here. Now that I put a big 2 in front of here, I'm getting two NAs and two NO3s. There's my two NO3s. How can I get there to be two NAs over here? I put a big 2 in front. And in doing that, I'll get two NAs and two Cls, and there are my two Cls that I balanced. Now I know I showed a bit of back and forth here about like what am I doing and how am I writing my ions. Whatever works for you, I would first say what compound am I making, write it down, and then balance the equation. Or if you know that, oh, I needed another Na here, and then I need another Cl on the other side, you could do that. But this is how we write and balance chemical equations. This is what we do with the ions. And I'm hoping this is an intense crash course on doing that. In my next video, I'll focus more on acid dissociations and then using buffer calculations.